In the last lecture, using Maxwell's equations, we formed a wave equation and had seen how these EM waves propagate in an infinitely extended dielectric medium. In this lecture, we will further look into the propagation of EM waves in dielectrics. The outline of the lecture is, we would again look into electric and magnetic fields associated with light waves. What is polarization? What is the energy associated with these waves? And we will define a vector called Poynting vector for this. Then if the EM wave encounters a boundary, if they go from one dielectric to another dielectric, then what are the conditions they should meet at the boundary of two dielectric media? And then we will look into some intricacies in total internal reflection, which will become very handy when we will do wave analysis or EM wave analysis of optical waveguides. So, what are the electric and magnetic field associated with a light beam? Well, we have seen that for a linearly polarized wave which is polarized along x and propagating along z, I can write the associated electric field as x cap E0 e to the power I omega t minus kz, and h is equal to y cap h0 e to the power I omega t minus kz, where the amplitude of h can be related to the amplitude of E by this expression. If I have electric field, then I can find out magnetic field from this expression, and if I have magnetic field, I can find out electric field by this expression. So, if I know one, other can be found out because they are interrelated. When we work out some real quantities, then instead of using phasor notation, it is useful to use the real part of these, and then I can write E as x cap E0 cosine omega t minus kz, and h is equal to y cap h naught cosine omega t minus kz. When I plot them, they look like this. Since E is along x, then E goes like this, the red curve, and the direction of vibration of electric field vector is given by these green arrows. The electric field is vibrating along x, and correspondingly the magnetic field is vibrating along y, okay, and it is represented by this blue curve. What I can notice here is that these E naught and H naught, they are real, and since they are real, because it is dielectric medium, lossless medium, then since they are real, then the electric and magnetic fields are perfectly in phase. So when E has a maximum, H also has a maximum. When E goes down to 0, at the same instant H also goes down to 0. So they are perfectly in phase. What is the velocity of this wave? In the previous lecture, we had seen that omega over k is nothing but 1 over mu epsilon naught, and this is the velocity with which the surface of constant phase are moving. So these are so this v is nothing but the velocity of the wave, and let me find this out for free space. For free space, mu is equal to mu naught and epsilon is equal to epsilon naught, and I can approximate mu naught by 4 pi times 10 to the power minus 7 and epsilon naught by 10 to the power minus 9 divided by 36 pi. And if I work this out, it comes out to be 3 into 10 to the power 8 meters per second, which is nothing but the velocity of light. And that is how it has been established that light is an electromagnetic wave. What is the refractive index of dielectric when these waves move in, if these waves move in free space and then the wave go in dielectric medium, we find that they have different velocities. So, this difference in velocities can be associated with what is known as a certain property of the medium, which is known as refractive index of the dielectric, and it can be given by C by V, which is square root of mu epsilon over mu naught epsilon naught. And since for all the dielectrics they are non-magnetic, so I can approximate mu by mu naught. So, n comes out to be square root of epsilon over epsilon naught, or I can write epsilon of a dielectric medium as epsilon naught times n square, where epsilon naught is the permittivity of free space. We see that electric and magnetic fields, they are interdependent. You have time varying electric field which generates time varying magnetic field, and this time varying magnetic field in turn generates time varying electric field. So, there is mutual generation of electric and magnetic fields, and it is due to this mutual generation of electric and magnetic fields EM wave propagates even in free space or in vacuum. They do not require any medium to propagate. Now, let us look at what is the meaning of polarization. If the electric field vector associated with an EM wave vibrates in x direction, the oscillations are in x direction, and there is a propagation in z direction. It is something like this. If I take a string, I attach one end of the string on the front wall, and then one end I shake in x direction. So, I am vibrating the string in x direction and generating the wave in z direction. So, this x, which is the direction of vibration of my hand or this end of the string, or here it is the electric field, it is the direction of polarization. And the electric field in general now can be given by of x polarized wave as x cap E0 cosine omega t minus kz plus phi, where phi is an arbitrary phase. It decides where you start your clock. So, I can also write this down as in terms of x, y, z components of electric field as Ex is equal to E0 cosine omega t minus kz plus phi, Ey is equal to 0 and Ez is equal to 0. Ez is of course 0 because they are transverse waves. Correspondingly, I can get the components of magnetic fields. Now, Hy would be H0 cosine omega t minus kz plus phi, Hx would be 0 and Hz would be 0. So, this is x polarized wave. I can also shake the string in y direction. Instead of x direction, I can shake the string in y direction and then the wave goes something like this. It again travels in z direction, but now the displacement is in y direction. So, your E is now y cap E0 cosine omega t minus kz plus phi, or you can again write them down in terms of the components of electric and magnetic field, and these are the components you will get corresponding to this y polarized wave. Now, if I take a transverse plane, here it is xy plane, and notice the vibration of electric field vector, Then in X polarized I see that the vibration is like this. For Y polarized the vibration is like this, but I can also shake the string in this direction. This is X, this is Y, but I can shake it in this direction also. Then I will create a wave which goes like this. The direction of vibration is now slanted. It makes certain angle, say theta, from x axis. Then this I call a linearly polarized wave which has both the components x and y. In this case you have only x component, in this case you have only y component, but you can have x and y both components. And the amplitude of these components will depend upon what is the direction of vibration of electric field vector. So, these are some examples of linearly polarized light. I have another possibility. I can shake the string like this. Again, the movement of my hand is confined to xy plane, and I am shaking the string like this, and I generate a wave like this. Okay. Then it is known as circularly polarized light. So, if I trace the variation of the tip of electric field vector on a transverse plane, it will go like this. So, how can I represent it? Since it is a circle, so intuitively I can say that if Ex is equal to E0 cosine omega t, then Ey should be E0 sin omega t, so that Ex square plus Ey square gives me some E naught square, which is the equation of a circle. If I now find out how the tip of electric field vector goes in xy plane, I plot this at t is equal to 0. At t is equal to 0, I will have Ex is equal to E0, Ey is equal to 0. So, I will be somewhere here. At t is equal to pi over 2 omega, I will come here. T is equal to pi over omega here, t is equal to 3 pi by 2 omega here. So, as time passes, it moves in this direction. This is clockwise. So, the direction, if the direction of propagation I have fixed as plus z and rotation is clockwise, then I can call this as circular right circularly polarized light, or RCP. It is a convention whether you call it right circularly or left circularly. So, if you call this as right circularly, then that one which is anti-clockwise and direction of propagation is plus z always, then it would be left circularly. So, I call it RCP. Then we often hear term unpolarized light. What is unpolarized light? Well, if at one instant I look at the direction of electric field vector, if it is x, and the next instant it becomes like this, and another instant it becomes like this, and then like this, then I do not have any correlation between the direction of electric fields at different instances. They change their direction randomly. Then such kind of light is known as randomly polarized light or unpolarized light. People call it unpolarized light, but I prefer to use randomly polarized light. Then what is the energy associated with an EM wave? For that, let me consider taking divergence of this E cross H. You may think, why suddenly I am taking the divergence of E cross H? Well, I want to find out energy associated with an EM wave, and right now I am considering medium which is isotropic medium, and in an isotropic medium what I have, the energy flows in the direction of wave. Wave is propagating like this and energy also flows like this. And I know that E cross H represents the direction of flow, direction of propagation of wave. It is in the same direction as the wave vector. And I also notice that E is I take E cross H, E is volts per meter and H is amperes per meter. So, V times A, volts times ampere will give you power. So, it is power per meter square. So, it is kind of intensity. So, it has got the units of power per area, power per unit area. Let us say S, and if I want to find out power, then I should multiply it by S. So, what I should do if I take the entire cross sectional area, so I do this and integrate it over the whole area. This E cross H dot ds from divergence theorem, I know that it is equal to divergence over integral over whole volume V, which is enclosed by this surface, times divergence of E cross H dV. V is the volume. So, this basically will give me the power flowing out. Okay. That is why I consider taking divergence of E cross H and see by using now Maxwell's equations whether it really represents the power or not. So, I take divergence of E cross H, which I can expand now as H dot del cross E minus E dot del cross H, and from Maxwell's equations I know del cross E is minus del B over del T and del cross H is equal to J plus del D over del T. So, this del dot E cross H can now be written as, because it is minus del B over del T, so minus mu times del H over del T, mu comes here. So, it becomes H dot del H over del T, and here you have J, here you have E. So, E dot J or minus J dot E, here minus epsilon times E dot del E over del T. So, this I can also write as H times del H over del T can be written as half of del H square over del T. So, this del dot E cross H can now be written something like this, Now, let me take this del T outside, then it is half mu H square plus half epsilon E square minus J dot E. What is this? We know that half mu H square is nothing but the density of energy stored in magnetic field, and this is nothing but the density of energy stored in electric field. What is J dot E? J is current per unit area, this is current density, and E is volts per meter, potential divided by the distance. So, this is nothing but power, V times I is power and A times D is volume. So, this is nothing but joule loss per unit volume. So, if you have a resistor, so P would be the power dissipated in resistor per unit volume. So, this is ohmic loss or joule loss per unit volume. Now, let me represent this E cross H as S, some vector S, and this energy density as U, which is the density of stored energy in electromagnetic field, then I have this, and let me integrate it over the whole volume, then I get this is equal to minus del del T U dV minus J dot E dV. Alright. So, this is what it is again here. This is nothing but the rate of decrease of energy stored in EM field. Okay, U times dV will give you energy, and this is nothing but the rate of Joule loss. So, this S, what is S now? I can now interpret S. So, this S is nothing but here, if I look in this form S dot ds, it is nothing but the flux of this vector S through closed surface S, which encloses this volume V. If I look at this, so if this is the volume and this is the surface area S, and I have some power P in, some power P out, then this is the net outward flux through this volume. And what is happening here? I have the stored electric energy, stored magnetic energy, and Joule loss. Okay. So, this S can now be interpreted as the energy per unit time per unit area which flows out. So, this vector has a magnitude which shows you energy per unit time per unit surface area, or power per unit area, or intensity, as I have seen here, and its direction is perpendicular to E and H, which is in the direction of K. Okay. And this vector is known as Poynting vector and represents intensity associated with an electromagnetic wave. So, this would be useful when we will calculate the energy associated with modes. Another useful thing would be, which we will use in our further analysis of optical waveguides and fiber, are boundary conditions. Okay, what are the boundary conditions? If I have two media, medium 1 and medium 2, these are dielectric media. Medium 1 has dielectric permittivity epsilon 1, medium 2 has dielectric permittivity epsilon 2, and if there is an electromagnetic field here, then if I know the field here, I can find out the field here, or I can relate the field in region 1 to field in region 2 using some condition. Okay. With what condition I can relate the fields here with the fields here? So, if I consider that the electric field here is E1, let us say in this direction, and electric field is E2, let us say in this direction, then these fields I can always break into two components. One is tangential to this surface interface, and one is normal to this. So, for E1 as well as E2, and then I can try to find out the relationships between these tangential and normal components. For that, what I do, I consider a closed loop something like this, A B C D A, and I know that E dot dl over this closed loop should be equal to 0. If I apply this, I go from A to B I need to take tangential component to the surface. So, it is E1t times delta W is the path. This is a very small loop, okay, so that it can represent a point when delta W and delta H tend to 0 and a surface and an interface when delta H tends to 0. Then I have from here to here, let us say it is delta H by 2 here, delta H by 2 here. So, E1 normal components times delta H by 2, then minus E2n delta H by 2, E2t delta W, E2n delta H by 2, E1 and delta H by 2. So, if I do this, I find that E1t should be equal to E2t. So, the tangential component of the field here and the field here, they should be continuous. The tangential component of electric field should be continuous. What about normal component? For normal component, I consider a pill box like this, very small pill box. Let me take initially the height delta H and it has got some surface area delta S. And I consider D1 and D2 vectors here. They are dielectric displacement vectors. I again resolve them into the components which are parallel to the surface and perpendicular to the surface. Now, in this small pill box, I apply Gauss's law, which gives me D dot ds should be equal to 0. When I do this, then I find this that it would be D1n times delta S. This is D2n times delta S with a negative sign. And what is the flux through this curved surface? This flux through this curved surface would be 0 as delta H tends to 0 to obtain this boundary, to close down to this interface. So, this gives me D1n is equal to D2n, which means that normal component of D should be continuous. So, I have got tangential component of E should be continuous and normal component of D should be continuous at the interface of two dielectric media, provided that there are no free charges at the interface, and this is true in case of dielectrics. There are no free charges, no free currents. In a similar way, I can show that for magnetic fields, the tangential component of H and normal component of B should be continuous. So, these are the boundary conditions that I will use whenever I will encounter an interface between two dielectric media. Now, lastly, let me revisit total internal reflection and understand some intricacies. You remember that when I did the ray theory simply tells me that a ray goes like this and it comes back. There is no energy which flows out into this medium. If this is the medium of refractive index N1, this is of N2 where N2 is smaller than N1, then ray theory tells me if I launch a ray which makes an angle larger than the critical angle, then this ray will come back into the same medium and there would be no transmitted ray in this. But if I talk about waves, okay, and with waves, these are EM waves, associated electric and magnetic fields. Let me assume that there is some transmitted wave also. There is some transmitted wave and then find out what would be the nature of that. So, first of all, I would ask, would there be any transmitted wave, and if yes, what would be the nature of that? So what I do, I let that there be a transmitted wave which is coming out at an angle I2. So, if this is N1, this is N2, this is the interface and this is the normal, this is the incident one at I1, and let me say here I have at I2, this is the transmitted one. So, the field associated with this would be given by E2. Let us say E2 is the field here, E2 is the field associated with this wave, these are waves not rays, would be now E2 0 e to the power I. Now since it is in xz plane, this is z, this is x, okay. So this is in xz plane, so I will have a component along x of wave vector which is k2x, okay. K2 is like this, so here you will have k2x and here you will have k2z, okay. So I will have e to the power I k2x times x plus k2z times z minus omega t. What is k2x? K2x is nothing but k2 cosine I2, this is I2. So that is what I have written, k2 cosine I2 times x, and similarly this is k2 sine I2 times z minus omega t. If I apply Snell's law here, then I know that sine I2 would be n1 over n2 sine I1, so I will get sine I2, and correspondingly cosine I2 would be 1 minus n1 square over n2 square sine square I1, and from here if I take this n1 over n2 out, so this would be n2 square over n1 square minus sine square I1, and since this I1 is greater than phi c for total internal reflection, so sine I1 should be greater than n2 over n1. If sine I1 is greater than n2 over n1, then this quantity would be imaginary. So I will have this cosine I2 as some I gamma times n1 over n2. Let me represent this as I gamma, which is imaginary now. So now if I put these values of I sine I2 and cosine I2 back into this, what I get that alright, corresponding to z it is fine k2z n1 over n2 sine I1 minus omega t, but corresponding to this I have I gamma factor, and this I gamma when it is multiplied by this I, it becomes exponentially decaying. So I will get some e to 0 e to the power minus alpha x times this, where alpha is this. So what I have got? I have a transmitted wave whose amplitude decreases with x exponentially. So I have a transmitted wave whose amplitude decreases exponentially in x direction. This is known as evanescent wave. So with total internal reflection, there is an associated transmitted wave in lower index medium whose amplitude decreases exponentially, and this wave is known as evanescent wave. This is going to be useful when we will do the analysis of optical waveguides and optical fibers. Thank you.